Welcome to lecture number 10. I devoted the last two lectures to the discussion of a certain global refinement that I denoted little m capital O of the unequivariant Thom or Bordism spectrum, which is traditionally called MO. In the last lecture I showed that little m capital O is globally connective, and I calculated the zeroth homotopy group global functor. It is cyclic as a global functor, so it's a quotient of the Burnside ring global functor by a single relation, but in the global sense, namely that the transfer from the trivial group up to the group of two elements, also known as the group O of 1, is trivial. I also gave a heuristic interpretation of how you can think of little m capital O as a global homotopy type. The rank filtration and the identification of the subquotient and the identification of how one piece is obtained from the next by attaching a copy of the global classifying space of an orthogonal group. All this together gives the interpretation that you can obtain MO by inductive procedure, where you start with the sphere spectrum and then from one step to the next you kill in a global fashion one specific and prominent equivariant homotopy class, namely the dimension-shifting transfer from OM-1 to OM of a certain class that also plays an important role for other things, the so-called inverse Thom class of the tautological representation of OM-1. So this is informally how you get from the m-first piece in the rank filtration to the mth piece. You do this inductively for all natural numbers m, and then the co-limit is little m capital O. Today I want to talk about a different global refinement of the unoriented Bordism spectrum, the one that I denote capital M capital O, and in the printed references this will all be boldface font. This is non-equivariantly equivalent to little m capital O. I will show this a little bit later today, but it is equivalently and globally very different. So for example, while this version is globally connective, this one definitely is not globally connective. In fact, it has a property that is inconsistent with being globally connective, namely it has Thom isomorphisms for equivariant vector bundles. So it's in this sense a globally oriented theory. It comes with Thom isomorphisms for equivariant vector bundles. This MO also has a unitary or complex cousin that I denote by a boldface MU. This is a global refinement of what's traditionally called MU, the unitary Bordism spectrum. That's also a very interesting, maybe even more interesting global homotopy type. Nevertheless, I will concentrate on the orthogonal version in this talk today. Let me give you the definition. The Vth space of the orthogonal spectrum capital M capital O is again a Thom space. MOV is the Thom space of the Grassmannian of V planes in V plus V. So again, Thom is referring to the tautological dim V plane bundle over this Grassmannian. If you recall the definition of little m capital O, we had V plus R infinity instead of V plus V. This might look like only a minor difference in the definition, but this small difference in the point-set level definition has drastic consequences for the equivariant and for the global homotopy types. The structure maps are defined in a way very similar to little m capital O. So I have to give you a map from OVW, the space in the indexing category for orthogonal spectra, smash MOV to MOW. An element in here is a pair W, phi, where phi is a linear isometric embedding from V to W. W is orthogonal to the image of phi. An element in here is an x, L, where L is a v-dimensional subspace of V plus V, and x is a point in L. And I'm sending this to the following expression. I'm sending this to W, 0 plus phi squared of x. So W, 0 lies in W plus W. Phi squared applied to x, which lies in V plus V, also lies in W plus W. These state in orthogonal summands. And I'm taking this relative to the subspace phi squared of L, and then again to get the dimensions right I have to add something, namely I add the orthogonal complement of the image of phi plus 0, where this is again a subspace in W plus W, and I view this as sitting in the first cement. So this is very similar to the definition of little m capital O, just that there is a V instead of an R infinity here. In particular, these two copies of V are not symmetric. One of them is preferred. It sort of carries the suspension coordinate. That's the first copy that carries this. The little m capital O had a ring spectrum structure, but it has an E infinity ring spectrum structure that I did not make explicit. This capital M capital O is a little bit better. It even has a strictly commutative multiplication. So it is what I like to call an ultra-commutative ring spectrum. So MO has a strictly commutative multiplication. So that should be a morphism of MO smash MO to MO, which I can give to you in the external form. In the external form I have to give you a bunch of maps for all inner product spaces V and W, from MOV smash MOW to MOV plus W, and these maps are essentially given by orthogonal direct sum. More precisely, an element in here is a subspace L of V plus V and a vector x in L. Here I have a y n, and I would basically like to send this to x comma y and L direct sum n, just that these don't quite live in the correct place, because L plus n lives in V plus V plus W plus W, and we should be getting something that is in V plus W plus V plus W, but that is of course easy to fix. So I take the preferred isometry that we will probably all think of first, which sends V prime W W prime to V W V prime W prime. So it switches these two factors, and I just apply it to get the syntax right, so that this lives in the right place. I leave it for you to check that these maps are associative, commutative, and there's a unit. The unit map has to be a base continuous OV equivariant map from S of V to M of V for every inner product space V, and then there has to be a bunch of coherence conditions, and we're sending this to the vector V, comma 0 in V plus 0. As I said, the two copies of V are not symmetric. One of them is singled out. The first one, it sort of carries the suspension coordinates, which you can see from this description of the unit map. As I already said in the introduction, this is important, for example, because it has Thom isomorphisms for equivariant vector bundles. I will not give you a complete proof. This is something I discussed at least for finite groups last semester, but I do want to remind you of what the Thom classes look like and how you can construct them. Here's how the Thom isomorphism in equivariant MO-cohomology works out. Suppose we have a vector bundle, an equivariant vector bundle. So let G be a compact Lie group. B a compact G space. And Xi from E to B, a rank n G equivariant real vector bundle. So there's a complex version of this, and for complex vector bundles you should consider the unitary analog, the boldface MU instead of MO. So because we have a compact G space, every such vector bundle can be obtained by pulling back a tautological bundle over a Grassmannian. So we choose a classifying map. So let psi from the base to the Grassmannian of n planes in V be a G equivariant classifying map. Continuous, of course. for some G representation V. i.e., what does this mean? So that psi is isomorphic to the pullback along this map, psi upper star of the tautological n-plane bundle, equivariant vector bundle over this Grassmannian. So the data of such an isomorphism can be slightly rewritten. So there's a map covering the map over the base. I write psi bar for this. So that psi bar. So this will be a map from the total space of the bundle to V. Be a fiberwise linear isometric, fiberwise linear embedding, and G equivariant, covering the psi below. So over every point in the base we have a vector space here, and we're assuming that over this, for this vector space, it's a linear embedding. Altogether it's a G map, and this covering condition means that if I take this lift phi tilde applied to a point in the total space, this will be a vector in V. This has to lie in the subspace singled out by the classic phi map psi if I apply this to the point in the base where I project down the vector V. So this data we can always find, and it's unique up to homotopy after possibly stabilizing, going to some larger representation. From this data we can produce a continuous based G map. From SV smash the Thom space of Xi, the one-point compactification of the total space, to the Grassmannian, the Thom space over the Grassmannian of dimension V plus n planes in V plus Rn plus V plus Rn, and V plus Rn exactly has the dimension dim V plus Rn, so this is exactly the space, the V plus Rn space in the spectrum MO. And how do we get this? So an element in here is a vector in V, smash a point in the total space, and I'm sending this to the following. So I have to give you a subspace in here, and then a point in the subspace, and the point comes first, and there I take little v, that's this V, 0 in the first R copy, then this lift, psi tilde of E, and then 0 again in the next copy. And as the space in which this lies, I take V plus 0 plus, and then the n-dimensional subspace singled out by the classifying map, and applied to whatever the point E sits over, I project it down to the base, and then plus 0. So this is a subspace of the appropriate dimension, and this is a point in the subspace. And of course infinity goes to infinity, so this is a continuous based G equivariant map. And this continuous based G equivariant map represents the Thom class for which I will write sigma G, Xi. And where do I want this to live? I want this to live in the co-limit over all W running over finite dimensional subspaces over the complete universe, the same kind of co-limit that we've seen before, for example, in the definition of equivariant homotopy groups. And then I take as W smash the Thom space of Xi, and then MO plus Rn G equivariant maps. And for this I write the nth cohomology G equivariant of the Thom space of Xi, and reduced because we're in the base situation. So the W is the thing that runs, so these two W's cancel out. This Rn, the target, is an n-fold shift, it's cohomological degree n, and this Thom space is it's a cohomology theory, it's in the contravariant variable, so this is a reasonable and the correct definition. Well, at some point I will restrict to the situation where the base is not just compact, but actually a finite GCW complex. Otherwise, I cannot control this homotopically very well, but I will restrict to that in a second. So this is the Thom class. Now there's a bunch of things to check. namely that this class is independent of the choices, and as I said, this essentially comes down to the fact that this classifying data is unique up to increasing the V by going to larger representations and up to homotopy. The Thom isomorphism theorem can now be formulated, and for this Thom isomorphism theorem, the module MOG upper star of B module MO star G of Thom space of Xi. So here I want the reduced theory, here I want an unreduced theory where the definition would be like this but with a disjoint base point added. It is free of rank 1, generated by the Thom class. So if you wonder how is this graded abelian group a module over this graded ring in the first place, so I told you earlier that MO is a strictly commutative ring spectrum, so that means the cohomology theory on a space with a disjoint base point is naturally valued, ring valued. And the Thom diagonal, which is a coaction of the base on this Thom space, induces it by the contravariant functoriality and by the multiplicatively the fact that MO has a commutative multiplication, a module structure of this graded abelian group over this graded ring. In cohomological degree n sits the Thom class, and this is a free module in the graded sense over this graded ring on the Thom class. I did not prove the Thom isomorphism theorem last semester, and I will not prove it today either. But last term I proved a special case of it, from which the general case essentially proves by a cellular induction on the GCW structure of the base G. So let me remind you of this special case. So when the base space is just a single point, and then a G vector bundle is essentially a representation. So more precisely, the total space of the bundle is just one linear space with the G action, and the reference map to the base is no information. And the Thom class then lies in the following group. I just write sigma G, V for it, and it lies in the reduced n-dimensional G equivalent cohomology of SV, because that's the Thom space for V considered as a vector bundle over a point. The Thom isomorphism theorem can be interpreted as saying that these classes are units in the ROG graded equivariant homotopy ring. You know, I didn't talk about ROG gradings very systematically, and I also won't do this in the future, but maybe you've heard about it, and this would be an ROG graded class of dimension V minus n. And the fact that it's a free generator means that it has an inverse in the ROG graded sense. In particular, the fact that these are ROG graded units means that the ROG grading is actually not more information than the Z grading in this particular example. So whenever you are oriented for all vector bundles, in particular for representations, then the ROG grading doesn't contain more information. So the way I showed the Thom isomorphism in this special case is by exhibiting an inverse. The inverse Thom class, for which I write tau GV. So this is a reduced G equivalent homology theory of SV. So this is just pi n G equivalent of MO smash SV with G action coming from here. MO is a global homotopy type. So this can be defined explicitly. It is represented by the following G map. It's a map from S to the V plus Rn, and this is the dimension of the representation, to the Thom space of the Grassmannian of V plus n, or in other words, 2n dimensional subspaces of V V plus Rn plus D plus Rn, and then smash SV. So this is really MO at V plus Rn, and then smash SV. So G equivalent map of this form. The thing that's running is V plus Rn, that's this V plus Rn. Here's an extra n, that's the n in the topological dimension, and here's an extra V, that is the coefficient, so I just have to give you a map like this. And the map we take, it takes x, v, x, y to the following. Again, I have to give you a subspace in here and a vector in that subspace. The vector will be 0, x, 0, y, and this would sit inside 0 plus Rn plus 0 plus Rn, and the V that we had here simply smash in there. So that's a G equivalent map that represents a class in here. I showed by explicit homotopies, like multiplying out the two representatives and giving the explicit homotopy, that the product, or the external pairing or Kronecker pairing of this class with this class is 1, and that proves the Thom isomorphism in this special case for representations over a point. To make this plausible, maybe you remember that the sigma class was defined by using the V and the V, and this other class is defined by using the R and the R, and this will sort of cancel after you've properly multiplied out everything. Now I would like to explain why orientability, so Thom isomorphisms for equivariant vector bundles, is essentially incompatible with being globally connective or equivariantly connective. After all, I'm claiming that this MO is not globally equivalent to the little m capital O, and I will show this by showing that this one is not equivariantly connective, not globally connective, and hence they cannot be globally equivalent. For this I want to remind you of what Euler classes are. So we have a vector bundle as before, that xi from E to B be rank n G vector bundle. As before, B is a compact G space. Then we have the zero section of the Thom space, let S from B plus, to make it a based map, to this Thom space of xi be the zero section, sending a point in the base to the point 0 in the fiber over it. That's a G equivalent based map. And then the Euler class is just a restriction of the Thom class along the zero section. So the Euler class of xi is the following. For this I will write E, G, xi, and it's just S upper star, so we're using the contravariant functoriality in cohomology applied to the Thom class, sigma G V, and this will lie in the MO-cohomology group in dimension M, now unreduced of the base. So in particular, if we do this for a representation, for B equals a point, and then we confuse vector bundles with representations. So this is where the Thom class this lives. This gives an Euler class. Which I write E, G, V, and this will now lie in MO N G equivariant of the point. That's the base, but this is the same as the homotopy group in dimension minus N G equivariant of MO. I will write down a proposition that says that this Euler class is generically non-zero. It's even better than that. In particular, this will show that there are non-trivial equivariant homotopy classes in negative dimensions, so MO is not equivariantly connective. Now, it's not the case that this is non-zero in general. For this, we have to assume that there are no fixed points. So here's the proposition. Let G be a compact Lie group. And V a G representation with trivial fixed points. And then the image of the Euler class under the geometric fixed point map phi upper G. This is the map which goes from the equivariant homotopy groups of MO to the geometric fixed points homotopy groups of MO. And this is a unit, an invertible element. In particular, the Euler class VGB is non-zero because we can relatively easily show that these geometric fixed points can be expressed in terms of non-equivariant Bordisms of Grassmannians, and this is non-zero. So if you have a unit in something that's non-zero, then the unit can't be zero, and so it couldn't have been zero before. So the argument I will give on the next whiteboard, it will basically just use various formal properties. We have a ring-valued theory here. MO is represented by a commutative orthogonal ring spectrum. In such a situation, this is a graded ring, this is a graded ring, and the geometric fixed point map is a graded ring map, and we will basically use some formal properties like this on the next whiteboard. So the argument behind this is more general, and it's essentially saying that Thom isomorphism or equivariant global orientability is inconsistent with being globally connective. I would like to show that for every representation V of a compact Lie group G with trivial fixed points, the image in the geometric fixed point homotopy group of the Euler class is a graded unit in this graded ring. And in particular, because that is non-zero, this is non-zero. So for that to have some content, we should better have a G representation that itself is non-zero but has zero fixed points, but this always exists as long as G is not the trivial group. Now, of course, for the trivial group, all representations are trivial, and only the zero representation won't have any content. But as soon as the group is non-trivial, we can find a non-zero V with this property, and thereby we get a non-trivial element in the negative dimension homotopy groups. So let me give a sketch proof, which again means that I'm not completely formalizing everything, but I want to give you the main mathematical idea behind this. The thing that is not completely formalized is that in the proof I do want to use ROG graded homotopy groups without saying completely carefully what they are. But let me use the following ad hoc definition. So for G representations V and W, I define a version of ROG graded homotopy groups. So I define pi V, W, G equivariant of X. So X is an orthogonal G spectrum. I define this as the co-limit over all U, finite dimensional subrepresentations of the complete universe. And then I take as V plus U, comma, X and W plus U, G equivariant based maps. The stabilization procedure is essentially the same as when W isn't there, where I would be, and W isn't there and V is R to the n, where I would be defining the nth equivariant homotopy groups. So this U is a running variable, the V is in the front and the W is in the back. And you can think of this as the ROG graded homotopy group indexed by the virtual representation V minus W. But there are some well-known pitfalls in this. When you actually want to grade by classes in the real representation ring, it's possible, but you have to be very careful. I am circumnavigating these pitfalls by actually indexing by the pair and not by the class of the virtual difference. So, of course, some special cases of this are if I take pi Rn, comma 0 G equivariant of X, this amounts to the nth G equivariant homotopy group of X. And if I take pi 0, Rn in the other variable, G of X, then I have a shift in here, so this is the pi minus n G equivariant of X. So the integer graded equivariant homotopy groups are in here as special cases. The next thing is that the geometric fixed point map that I have previously discussed in the context of Z-graded homotopy groups extends to this. So geometric fixed point map extends to this context. To a homomorphism from pi G equivariant V, W of X to the geometric fixed point homotopy groups, but now in the dimension of Vg minus the dimension of Wg of X. So this is kind of an ROG graded thing. This is really just a Z graded thing. Here I'm talking about the dimensions of the fixed points. Strictly speaking, for this, this is just a number. For this to make sense, I would have to choose an identification of this vector space with R to the dimension and another one of this with R to the dimension, and there's some ambiguity in the sign. This is one of the things I'm not completely formalizing. The situation we care about, everything is a two torsion anyhow, so signs don't matter. But this is the kind of thing where I would have to be more careful if I really do fully formalize this. And the definition is the same as the geometric fixed point map in the integer, where you take an equivariant map and you take G fixed points off the representative, and that's going to be an element in here after you've appropriately identified these. Okay, so now we are in the situation, we want to find out something about this Euler class, that is a Z-graded class, but we're going to use the Thom class and the inverse Thom class as auxiliary tools, and those are ROG-graded classes. So in this situation, the sigma G, V with a new notation, it sits in pi V, Rn, G equivariant of MO, and its inverse, the inverse Thom class, G, V, sits in pi G, Rn, V of MO. Another pair of things that I'm sort of not completely formalizing, a little bit sweeping under the rug, is that there is some trace left of the fact that it's essentially an ROG grading. If you multiply representatives together, you have to add up the representations in the first variable and the representations in the second variable. But then if one representation occurs both in the second and in the third variable, you can essentially cancel it. This is what remains of the fact that you're essentially grading by the virtual difference of the two. So that means if I multiply these two together, it would lie in V plus Rn, Rn plus V, and those I could cancel to get a degree 0 homotopy class. Again, I'm not doing this completely formally. Another thing I will use is that everything is multiplicative, so if the orthogonal spectrum X happens to have a ring structure, for example, as now in the strongest possible sense, a commutative points at level multiplication, then these are all associative and in a suitable ROG graded sense commutative multiplications. So in particular, we can take the geometric fixed point homomorphism, apply it to sigma G, V, and then multiply with the image under the geometric fixed point homomorphism of tau, V, because the geometric fixed point homomorphism MO the ring spectrum is multiplicative. We get phi G of sigma GV times tau GV. This is phi G of 1 in pi 0 grading, and of course it's a ring map, so 1 goes to 1. So this is a relation. Where does this stand? This lies in the 0-dimensional geometric fixed point homotopy groups of MO. The next observation is that we allow ourselves the freedom to use this ROG grading and its multiplicativity properties. Then the Euler class can be expressed also as a product of the Thom class with something else. So the Euler class G, V can now be written as a class that's often denoted by A, G, V times sigma G, V, where this A, G, V is a class that lies in pi 0, V equivariant G of MO, which is really the same as pi 0 G equivariant of MO smash SV, and this is represented by the class going from S0 to MO0 smash SV, and it's just the fixed point inclusion. So MO0 is just S0. Here the fixed points are just 0 and infinity, and you're including this as the fixed points 0 and infinity. So this class actually arises already from the sphere spectrum, and I'm basically pushing it forward. The A class comes from the sphere spectrum, unlike the Euler class and the Thom class, and I'm pushing it forward along the unit of the ring spectrum structure here. Now, the next thing we observe is that if I take geometric fixed points of EGV, then by the multiplicativity, I can take geometric fixed points of A, G, V, times geometric fixed points of sigma, G, V. But what's happening here is that this is the inclusion of the fixed points. So V is a representation without non-zero fixed points. So the geometric fixed point map takes fixed points of this. So after I've taken fixed points of this, I get a homomorphism, and I essentially get the identity of S0 with S0. So this element is actually 1. So this all together is phi G of sigma G, V. But this element in the geometric fixed point homotopy group is a unit. Here's its inverse, the geometric fixed points of the inverse Thom class. So this is showing that this is the same as this, which is a unit. So this is the unit, and this is the end of the argument. As just explained, the orientability of the Thom spectrum capital M, capital O leads to negative dimensional homotopy classes, non-zero homotopy classes in the G-equivariant homotopy ring as soon as the group is non-trivial. In particular, MO is equivariantly not connective as soon as the group is non-trivial, and so it cannot be globally equivalent to little m capital O, where we showed that this is globally connective. I still owe you the proof of a different claim that I've made, namely that little MO and capital MO are non-equivariantly stably equivalent. In particular, capital MO is also a model of the unoriented Bordism spectrum. So to show this, I should produce for you a morphism that is a pi star isomorphism on non-equivariant homotopy groups, well, or at least a zigzag of such things. If you remind yourself of the definitions, here we took Grassmannians in V plus V. Here we took Grassmannians in V plus R infinity, and there doesn't seem to be a way to directly compare those. But whenever you want to compare two things and you cannot directly, then you should make a third thing, which sort of has the ingredients of both constituents in it, and with either projects to the two things you want to compare or receives map from them. And this is what we're going to do in the latter case. So we define morphisms of orthogonal spectra. One from little m capital O that I call A to something that I call MO prime, indicating that it's not isomorphic but globally equivalent to MO. And another one B in this direction, MO, with the following properties, such that A is a pi star E isomorphism, an isomorphism on non-equivariant homotopy groups, and B is actually a global equivalence. The thing in the middle, the MO prime, by definition combines the two features of the two. So MO prime at V is also, as before, the Thom space of a tautological bundle over the Grassmannian of V-dimensional subspaces. Now I'm taking V plus R infinity. So the V plus V I need to compare to this one, and the V plus R infinity I need to compare to this one. And again, I decide that the first V is the distinguished one. When it comes to the structure map, I have to single out one copy of V, and the structure map will work out in very much the same way. It's going to be this copy. And then we have linear isometric embeddings. The linear isometric embeddings on the one hand side from V plus R infinity to V plus R infinity, and the one I take sends V comma x to V comma 0 comma x, because I've decided the first copy of V is the distinguished one. And on the other hand, I compare this to V plus V in the most obvious fashion. I send V comma W to V comma W comma 0. So these induce maps on the Grassmannians. We always have the same dimension V here, and then also on the Thom spaces for the tautological bundles. So these induce based continuous maps that I'll call A of V So this goes from little m o v in this direction to MO prime of v, which is the Thom space of the Grassmannian over this one, and in that direction b of v, M of v. So these are base continuous maps, or v equivariant maps for every v. And as we let the inner product space vary, these are the morphisms of orthogonal spectra that I've written up there. So now what remains to do, other than you checking that these are really morphisms of orthogonal spectra, everything works out, which is not difficult here, are to check that this is a pi star isomorphism and this is a global equivalence. So let me do the first one. So proposition A from MO to MO prime is a pi star non-equivariant isomorphism. So this one is easy, easier than the other one, which is also not terribly difficult. And actually something a little bit stronger is true, namely it's actually a non-equivariant level equivalence. Okay, so since v plus r infinity to v plus r infinity, so this line up here is a linear isometric embedding between infinite dimension and r vector spaces. And the emphasis on infinite dimensional. It induces a homotopy equivalence on Grassmannians. The induced map from the Grassmannians of V planes in V plus R infinity to the Grassmannians of V planes in V plus R infinity is a homotopy equivalence. Both are classifying spaces for the orthogonal group dimension of V, and both admit CW structures. So this is a homotopy equivalence. And because these two spaces are also well behaved, they admit the structure of a CW complex, for example, and because the tautological bundle here is obtained by pulling back the tautological bundle here, the induced map on Thom spaces is also a based homotopy equivalence. So induced map of Thom spaces is a based homotopy equivalence. So this morphism A is even a non-equivariant level equivalence. But all of this work, because we're ignoring the fact that the orthogonal group of V also acts, we're also only considering all of this non-equivariantly. That's the proof of the first claim, and now it remains to prove that this is a global equivalence. To prove that the morphism B is a global equivalence, we're going to use an analog of the rank filtration, which we also have for the orthogonal spectrum MO prime. We define a filtration of MO prime by orthogonal subspectra by MO prime M at V, and now we do the expected thing. It's a Thom space over the Grassmannian of V planes and V plus Rm. So for the rank filtration of little MO, we had a single copy of V, and now we have two copies of V. So this gives us a filtration which starts with MO prime 0, and then there is no R to the M. So this is really the MO without a prime, sitting inside MO prime 1, and so on, MO prime M, and then the union for m greater or equal to 0 of the MO prime M's is the MO prime. So we want to show the map all the way from here to here as a global equivalence. This is a situation where we filtered by a sequence of closed orthogonal subspectra. So this is this kind of situation where equivariant homotopy groups commute with this co-limit. In particular, it suffices to show that each inclusion of one of the stages into the next is a global equivalence. It suffices to show that the inclusion from MO prime M into MO prime M plus 1 is a global equivalence for all M. Okay, to do this, I define another morphism of orthogonal spectra that I denote by kappa from MO prime M plus 1 smash S1, so the suspension, to the shift of MO prime M. And the way to think of this is that it's essentially a morphism backward in the direction of the inclusion. You know, the inclusion goes from here to here, this morphism goes in the other direction. You know, suspension and shift are globally equivalent but not isomorphic, but the role that this map plays is sort of backwards to the inclusion. And here is how we define it at V. V is in a product space. So here we have to start from MO prime M plus 1 smash S1 at V. So what is this? This is the Thom space of the Grassmannian of V-dimensional subspaces of V plus R n plus 1. That's this n plus 1. And then we have another S1. And it goes to the Thom space of the Grassmannian of V plus 1 dimensional subspaces, because shifting means we first have to put an R inside and then the dimension has gone one up, and then of V plus R plus V plus R. This means, because shifting means we have to evaluate at V plus R, and then there's another plus R to the M that comes from this M here. So this is the shift of MO prime M evaluated at V, and here is the map that I take. So an element in here is an x, L. L is the V-dimensional subspace of this, x is the point in that, and then I have a y. Y is another element of the real numbers. And I send this to, well, essentially I want to put the y in this R slot, and I want to spread out the rest out. So I want to take these two V's to this V and this V. The R that is outside goes to this place, and the R to the M is split up into the R and the R to the M. So that's the idea. And formally, I send this to J of x, y, comma J of L plus R, where J makes this spreading out in the way I've indicated precise. So J is a linear isometric embedding from V plus R to the M plus 1, that's sort of this, and then comes the R which belongs here, plus R, and then to V plus R plus V plus R plus R to the M, that's what stands here, and it sends V, W, comma x1 up to x M plus 1, comma y, to V, comma y, W, comma x1, and then x2 up to xn plus 1. So I'm just formalizing what I said in words a little bit earlier, how we spread out these coordinates. Now there's a bunch of things for you to check, that this defines a morphism of orthogonal spectra, and more importantly, that a certain diagram commutes. The following diagram commutes. I will not check this for you because it's boring. So I have MO prime M smash S1. Here I have the inclusion to MO prime M plus 1 smash S1. Here I have the morphism just defined, which are called kappa to MO prime M shifted. On the other hand, down here, there's this lambda morphism for the spectrum MO'(M) that came up previously, that's defined level-wise by the opposite structure map. And something I used before and where I gave you a reference earlier is that this is always a global equivalence. Down here, I can put the shift of MO'(M plus 1 and the inclusion here. This is a subspectrum of this. And here I can put the other lambda map. Here I can put the lambda map for MO'(M plus 1, and this too is a global equivalence. So now I'm in a situation, I have three composable morphisms, this one, this one, this one. I know that this composite is a global equivalence and this composite is a global equivalences. And global equivalences, because they are defined by going to isomorphisms under some functors, satisfy the 2 out of 6 property. 2 out of 6. And this implies if this is a global equivalence and this is a global equivalence, all the other three morphisms are global equivalences too. This one is, this one is, this one is. The one that I'm particularly interested in is this one. It's one of the ones. So in particular, MO'(M smash S1 included into MO'(M plus 1 smash S1 is a global equivalence. But then smashing with S1 has a suspension isomorphism. It just shifts the equivariant homotopy groups. So smashing with S1 detects and preserves global equivalences. So already the inclusion from MO'(M into MO'(M plus 1 is a global equivalence. And this finishes the proof. It was the last step needed to show that the morphism B is a global equivalence of orthogonal spectra. I would like to end this lecture with 3 different comments about the global Thom spectra, little mo and capital MO. And these comments are supposed to illustrate why these are interesting and important global homotopy types. So the first is about the connection between little mo and capital MO. One can say more than just that they are not globally equivalent. And here the slogan is that MO is the localization of little mo at the inverse Thom classes. So let me formulate a precise statement. First of all, we have this weak morphism of E∞ global ring spectra that I discussed on the last whiteboard. So there was this A, which was a non-equivariant equivalence, but not a global equivalence. And there was this B, which was a global equivalence to MO. So this has an E∞ multiplication. This has a strictly commutative or ultra-commutative multiplication. And this also has the weaker kind. It has an E∞ multiplication. And these morphisms are all multiplicative for the weaker kind, for the E∞ kind. E∞ multiplications are good enough to get external and internal pairings on the equivariant homology theories represented by this. So we get an induced map on homology theories, induced transformation on equivariant homology theories. So from MO star reduced G equivariant of A, where A is a based G space, we'd first go to here, but then the map in this direction is invertible because it's a global equivalence, so we can go on by first doing the effect of this and then the inverse of the effect of this to MO tilde G equivariant star of A. In here I discussed the Thom classes and the inverse Thom classes. I even gave you specific representatives for the inverse Thom classes of representations. So the inverse Thom classes can also be defined in here. Have distinguished pre-images, which are just as easy to write down in closed form as I did for capital MO. Pre-images that I usually note by the same name, and this lives in MO G equivariant of dimension as V, whereas before V is a representation of the compact Lie group G of dimension n. So the definition is similarly explicit in terms of representativeness. Here, the inverse Thom classes are inverses of the Thom classes, so here they are invertible in the ROG-graded sense. Here, the Thom classes don't exist, only their inverses exist, so here they are not invertible in the ROG-graded sense. This map is multiplicative, and it sends these classes to invertible ones, so it will automatically factor over the localization of this theory where we formally invert multiplication with all these invert Thom classes, which are not yet invertible here. And then the precise theorem, or one formulation saying that MO is the localization of little mo at the inverse Thom classes is the following. For every compact Lie group G, and based G space A, the homomorphism of graded abelian groups, or if you wish, morphisms over pi star G equivariant of MO, where I take the homology theory, G equivariant represented by MO on this base G space, and then I formally invert multiplication by the inverse Thom classes. Let me use the abbreviated notation for this. So this means a co-limit over all finite dimensional subrepresentations of the complete universe, and then you always multiply by the inverse Thom class. This transformation extends over the localization because the Thom classes are invertible here, and this goes to MO star G equivariant of A, and this is an isomorphism. I give you a reference to the global homotopy theory book where you can read this up and where all the terms are properly defined. There's a different interpretation for this, so informally, you can think of this as saying that MO is globally little mo 1 over tau. And there's actually a way to make this more rigorous and not just an informal statement. So this is a project of mine that I've even given a talk about. The weak map from little mo to capital MO is an E-infinity morphism. It inverts certain ROG-graded classes, and I can show that it is homotopy initial in the category of E-infinity global ring spectra among morphisms out of little mo which invert all these ROG-graded elements, these inverse Thom classes. It's relatively easy to show by formal nonsense that if you're given an E-infinity global ring spectrum and a bunch of ROG-graded classes, there exists a homotopy initial map to some other object in this category, E-infinity global, that inverts these ROG-graded classes. And then the punchline is that you can identify this localization in this particular example with capital M, capital O. My next comment is that the equivariant homology theory represented by capital M, capital O also has a geometric interpretation. This is a theorem of Bröcker-Hook. And it goes as follows: for every compact Lie group G, the Thom-Bandriagen construction induces an isomorphism from stable geometric borders to MO star G homology. This needs a little bit more explanation. So first of all, what is stable geometric Bordism? Stable geometric Bordism is a localization of the really geometrically defined equivariant Bordism, where you're inverting the geometric avatars of the inverse Thom classes. So there are specific classes in the G equivariant Bordism, geometrically defined, associated to a G representation V. It's basically the class represented by the unit disk relative to its boundary, which is a geometrically defined class. If you formally invert multiplication with these classes in the geometric equivariant Bordism theory, you get a new theory, which is called stable geometric Bordism. Classes in there are not in general represented by smooth closed G manifolds anymore, but they're sort of fractions of smooth closed G manifolds divided by representation. So in some sense they still have a geometric interpretation. These geometrically defined classes go to the inverse Thom classes under the Thom-Pontriagin construction. They're invertible here, so the Thom-Pontriagin construction that comes up in Wassermann's theorem will extend over the localization, and the theorem of Bröcker-Hook says that this is an isomorphism. Note that this is true for every compact Lie group. There's no restriction here, not just for finite times torus. This is a completely general statement. Here's a reference to the original paper by Bröcker-Hook, and I give you another reference to the global homotopy theory book, where I've written up a different proof of this theorem in a more global spirit. The very last comment that I want to make is that also the formal group law story has an equivariant version, and I think this is a very exciting development, and I just want to touch upon it very briefly. As I mentioned in the last lecture, Quillen had shown that the formal group law, the two-torsion formal group law that comes with the coefficient ring of MO because it's oriented, that this is the universal two-torsion formal group law, one-dimensional and commutative. So the canonical map from the Lazard ring for two-torsion formal group laws to pi star MO is an isomorphism. Even more important is the unitary or complex version, where it's the coefficient ring of MU and where it's general one-dimensional commutative formal group laws, not necessarily two-torsion. This is the beginning of chromatic homotopy theory, and it's extremely important since a couple of decades. Already some time ago, people have studied whether there are equivariant versions of Quillen's theorem. So there were definitions, for example, one proposed by Cole, Krish, and Greenlees of what equivariant formal group laws should be. Here you have to restrict the compact Lie group in question. So if you're interested in the integral version, then the compact Lie groups should be restricted to abelian compact Lie groups. The reason for this is that then all irreducible representations, complex representations, are one-dimensional. In the MO version of the story, you have to restrict to elementary abelian 2 groups. The reason is that for those, the irreducible real representations will all be one-dimensional. And then there were proposed definitions of what equivariant formal group laws and equivariant two-torsion formal group laws would be. And it's been an open question whether MO star in the two-torsion case and MU star in the complex case, and in the one case for elementary abelian 2 groups, in the other case for abelian compact Lie groups, carries the universal equivariant formal group law or two-torsion formal group law. In a recent preprint, Markus Hausmann showed that this is indeed the case, and I think this is a very interesting and exciting result. I just want to give you a reference because I'm not the person who should tell this story, but I encourage you to look it up. This is the end of today. Now I've devoted 3 lectures to discussing explicit examples in very much detail. In the next lecture I will return to some general properties, and I will start discussing the global stable model structure on the category of orthogonal spectra. This is all for today. Thank you for your attention.